So, I will start again with bilinear form. So, bilinear form of a Kac-Moody algebra. So, a matrix A, which is Aij n by n matrix, is called symmetrizable if there exists an invertible diagonal matrix and a symmetric matrix such that A can be written as dB. Okay. So, we have an invertible diagonal matrix and this is a symmetric matrix and A can be written like this, then we call A a symmetrizable matrix, and this is a decomposition of symmetrizable matrix A. Alright. So, B is called the symmetrization of A. B is called symmetrization and the corresponding Lie algebra GA, Kac-Moody Lie algebra GA, not Kac-Moody Lie algebra, corresponding Lie algebra. So, I will say once I am taking generalized Cartan matrix, then I can say this GA is a Kac-Moody Lie algebra. So, then GA is called the symmetrizable Lie algebra. Okay. So, we are fixing A is a symmetrizable Lie algebra, A is a symmetrizable matrix with the decomposition A is equal to dB, where D is diagonal epsilon 1, epsilon 2, epsilon n and B is Bij. And this A is Aij, and H pi check is a realization of A. Alright. Now, we consider this as H prime, which is C alpha I check, all these combinations, all of them, and we consider a complementary subspace of this in H. Okay. So, this is, so we consider a complementary subspace H double prime of H prime in H, and we define a symmetric bilinear form. We define a symmetric complex valued bilinear form on H. So, the form is defined in this way: alpha I check on an element with an element H, it is defined as alpha I H, this H, epsilon I for H belongs to H, I varies from 1 to n. Okay. And if I take two elements from H double prime, then we define it to be 0. For H prime, H double prime is coming from H double prime. So, this is the bilinear form. So, we can check. So, what is it on alpha I check on alpha j check? What is this? So, this is again we will use this, and this will become alpha I alpha j check epsilon I. Okay. And what is this? This is, because this is symmetric form, so we can write it alpha j check alpha I, and this is nothing but AJI. So, this is AJI, and from here we see that this implies AIJ is equal to epsilon I BIJ. Okay, from here. So, AJI is, so we have epsilon I epsilon j Bij, because Bij, this is a symmetric matrix. Okay. So, we have found out this. So, next thing is our lemma, which says that this bilinear form on H is non-degenerate. We will take it up in the tutorial. Okay, so let me write it down. So, this is a lemma which says the bilinear form on H is non-degenerate. Which is defined by this two. 1, I call it 1 and 2. So, defined by this bilinear form, defined by 1 and 2 is non-degenerate on H. So, this is an exercise. Alright, since this bilinear form is non-degenerate on H, so we have an isomorphism from H to H dual. So, since the bilinear form non-degenerate on H, we have an isomorphism nu from H to H dual defined by so nu H, this is an element of H dual. So, nu H on say H1, I take an element of H. So, this is H bilinear form H1. Okay. Because of this non-degeneracy, we have this isomorphism. So, now from here we can find out what is nu of alpha I check. So, what is this? So, what is this? So, we write nu of alpha I check with some element h belongs to h. This is by this, it is alpha I check h, right, and this we will be using this definition here. So, this is alpha I h epsilon I, and I can write this epsilon I here. So, this will be, yes. So, from here we conclude that nu of alpha I check is epsilon I alpha I. Okay. All right, and we have another induced form on H dual also. So, we have an induced form on H dual. So, using this one can see that alpha I alpha j is equal to so did I calculate this? Yes. So, from here one can see this alpha I check alpha j check is epsilon I epsilon j b I j. So, this upon epsilon I is just nu inverse of alpha I. So, this from here one can say that this is b I j, and this is equal to exactly a I j upon epsilon I, and this is for I j varies from 1 to n. So, we have a induced form on H dual also. Alright. So, this is a bilinear form on H. Now, there is a result, it is a theorem which says that we can extend this bilinear form on the entire Kac-Moody algebra. Okay, and that form one has to prove that this is non-degenerate, it is non-degenerate and invariant. There are certain properties. So, I will just state the theorem, we will not go into the details of the proof. So, we call it theorem, say theorem number 2. So, whatever I have said till now, this was true for any symmetrizable matrix. Now, I am considering symmetrizable generalized Cartan matrix. Okay. And so, in that case, if I am taking this A is symmetrizable generalized Cartan matrix, then corresponding Kac-Moody algebra is GA, and I am saying that we can extend this bilinear form from H to the whole of GA. Okay. So, in fact, I can do it only for symmetrizable Lie algebra. I will tell that later on. So, let A be a symmetrizable matrix with a decomposition A is equal to dB. So, this is the diagonal matrix, this is the symmetric matrix. Then there exists a non-degenerate symmetric complex valued bilinear form on GA. This is symmetrizable Lie algebra such that there are certain properties, so such that the form is invariant, okay, such that the form is invariant. So that means x bracket y with z, this is equal to x y bracket z. Okay, x y z belongs to ZA. So for every x y z belongs to GA. Now if I restrict this form to H, then this is the form which is defined by 1 and 2 and it is non-degenerate on H. So if we restrict this form, so again I am denoting this form by this, and I am restricting this form to H, then this restricted to H is defined by those two definitions 1 and 2 and is non-degenerate. Okay. So we are extending this form to whole of GA, and on H the definition is same and it is non-degenerate. Okay. And there are some 1 or 2 more properties. So third property, so third property is this bilinear form. If I take some element from G alpha and some element from G beta, so G alpha G beta is equal to 0 if alpha plus beta is not equal to 0. And the fourth one is, if I restrict this form to G alpha plus G minus alpha, then this is non-degenerate. Non-degenerate for alpha not equal to 0. And the last property is x bracket y is equal to bilinear form xy and nu inverse alpha. For x belongs to G alpha, y belongs to G minus alpha, and alpha is not equal to 0. Okay. Alpha is a root which is not equal to 0. So alpha is a root. We will be using this later on, okay, this part. So this we will be using it. So whatever I have told till now, this was true for any symmetrizable matrix A. Now I am restricting the same thing on a generalized Cartan matrix, symmetrizable generalized Cartan matrix. So in that case we have a simpler decomposition. So in that case these we can choose. So A is this diagonal epsilon 1, epsilon 2, epsilon n, and B if I am choosing symmetrizable matrix, generalized Cartan matrix, then we can replace these by positive rationals, and this is a symmetric rational matrix. So, this is a exercise, we can include this also in the tutorial sheet. So, when we are taking a generalized Cartan matrix, we have a simpler decomposition. So, this is these are all positive rationals, and this is a rational symmetric matrix. So, I will just write it. All right. So, I will.
In general case, we can get the non-degenerate form on H.
Sorry?
In general case also, we can get non-degenerate.
Yes, in the symmetrizable case, I am getting.
No, not in the symmetrizable. In general case also.
In general case.
It won't be symmetric, but we can get non-degenerate form. It's possible.
No, this is
So
necessary.
we are putting the symmetrizable conditions to ensure that that is actually symmetric bilinear form.
Yes.
So if we remove the symmetrizable,
Then one cannot talk about symmetric bilinear form.
yeah, we can get non-degenerate bilinear form.
Yes, maybe it is possible, but we cannot guarantee the symmetric part of the bilinear form. We have to check. Okay. So, we are considering, so if A is symmetrizable and generalized Cartan matrix, is diagonal epsilon 1, epsilon 2, epsilon n, and this B. So, these are all positive rational numbers. Positive rational numbers. In case we have this generalized Cartan matrix, and B is a symmetric rational matrix. Such a decomposition always exists. So, we have to see, I leave it as an exercise that such a decomposition exists. Okay. So, such a decomposition always exists. So, this is also another exercise for you. Okay. All right. So, now, so again, because the matrix is symmetrizable, we can again talk about this bilinear form. So, now what we can see in this case, so in this case, when all these epsilon 1 to epsilon n, they are positive rational numbers, what happens? So, alpha I with alpha I, what is that? What was? So, do you remember alpha I, alpha j is Bij. Okay. So, this is Aij upon epsilon I. Okay. Okay. So, from here alpha I is equal to aii upon epsilon I. aii is 2, so this is 2 upon epsilon I. This is positive, so this is greater than 0 for I varies from 1 to n. Okay, is this okay? And what about alpha I alpha j? So alpha I alpha j is aij upon epsilon I. This is positive. aij's are always negative, okay, less than or equal to 0. So this is always less than or equal to 0 for I not equal to j. All right. And what can we say about alpha I check? So we proved something else also. So nu of alpha I check is epsilon I alpha I. So from here what can we find out about alpha I check? So alpha I check is epsilon I nu inverse alpha I. And what is epsilon I? From here one can say that epsilon I is equal to, from here this equation, epsilon I is 2 upon alpha I alpha I. Okay. So we have concluded that alpha I check is equal to 2 upon alpha I nu inverse alpha I. Okay. And what about aij's? What about aij's? And aij is epsilon I alpha j from here. Okay. And epsilon I is again I can write 2 upon alpha I alpha I. Okay. So our generalized Cartan matrix A is given by 2 alpha I alpha j upon alpha I alpha I. This is the generalized Cartan matrix A. All right. So if I consider a symmetrizable generalized Cartan matrix, then we can extend the form from H to the whole of GA, and we use the same definitions, and this form remains invariant, non-degenerate, complex valued, and it is given by this. And if I say that I am putting this condition alpha I is greater than 0, then such a form is called standard invariant form. So I am putting this we have proved the condition, so I am including this condition, and we say that form has been extended from H to the whole of GA, and we are putting this, that alpha is greater than 0, such a form exists because of our theorem, and such a form is called standard invariant form on Kac-Moody algebra. Okay, so I will just state it. Okay. So, I state this standard invariant form. Okay. So, we are considering symmetrizable matrix and a generalized Cartan matrix. A is symmetrizable, generalized Cartan matrix, we fix, I am writing it again, we have done it already. So, we fix a non-degenerate symmetric complex valued bilinear form given by that equation 1 and 2, given by those 1 and 2. I wrote 1 and 2, right? So, 1 and 2 on H. This was on H, and we extend by that theorem to all over GA, and we extend this form to Kac-Moody algebra GA, and because of our theorem 2, such a form exists. Okay. Such a form exists by theorem 2, and if alpha I is greater than 0 for I varies from 1 to n, then this form is called standard invariant form. Okay. Then this form is called standard invariant all right. Okay. So, we have talked about the bilinear form. Now, I will tell you about the while group of Kac-Moody algebra. So, now I talk about while group of G. Okay. So, for each I from 1 to n, we define fundamental reflections. We define fundamental reflection Ri. So this is map from H dual to H dual, okay, and so this is defined as Ri on an element lambda belongs to H dual. It is lambda minus lambda alpha I check alpha. This is for all I varies from 1 to n. Okay. Now whether is it a reflection? Is it a reflection? It is taking alpha I to minus alpha I, and so it will be fixing all those elements for which this is 0, right. So its fixed point set is all those lambda in H dual such that lambda of alpha I check is equal to 0. Sorry?
In case of reflection,
Yes.
the mapping is Ri of minus lambda equals to minus of Ri of lambda.
No, Ri of alpha I will be going to minus alpha I.
Okay.
So we can check this Ri of alpha I. So you write here alpha I, here alpha I check alpha I. This is nothing but AII, okay. You remember this? This is nothing but AII, so that is 2. So this is just AII. So this is, I'll just so this is Ri of alpha I is equal to alpha I minus 2 alpha I, which is minus alpha I. Okay. So the subgroup, W of GL H dual generated by the fundamental reflections is called the while group of GA. All right. So yesterday I talked about generalized Cartan matrices. So I told that there are 3 types of generalized Cartan matrix. I will briefly tell you exactly those 3 kinds. So generalized Cartan matrix there are three types of generalized Cartan matrix. So, one is finite type generalized Cartan matrix, another is affine type, and third is indefinite type. So, so this is a notation which means, so this U, this is a column vector, so this is U1, U2, Un, and these entries are real numbers. So, U1, U2, Un are real numbers. So, U greater than 0 means all these Ui's are greater than 0, means all these Ui's are greater than 0 or all I. Okay. So, this is just a notation. So, finite type matrix means, so this is determinant, in this case determinant of A is not equal to 0. Okay. So, this is a rank n matrix and there exists alpha greater than 0 in this case such that A alpha is also greater than 0. Okay. So, alpha is, it's a column vector and all the entries are positive. So, what I am saying, there exists some alpha greater than 0 such that A alpha is also greater than 0. So, and in case of affine type we have determinant of A is 0 and rank of A is n minus 1. In this case, rank of the matrix A is n minus 1 and there exists alpha greater than 0 such that A alpha is equal to 0. And indefinite type, there exists alpha greater than 0 such that A alpha is less than 0. So, we will be talking about this case. So, this is, there exists alpha greater than 0 such that A alpha is less than 0. Okay. So, we will be talking about this case. So, corresponding Kac-Moody algebra in this case is called affine Kac-Moody algebra. So, this is of rank n minus 1. Okay. So, in this case what is the centers? I said dimension of center is n minus L. So, in this case center will be one dimensional. Okay. So, today I will tell you about this realization of this. So, in terms of loop algebra as central extension of loop algebras. Okay. We cannot say anything about that. It can be anything, we have no idea, because also not much is known about this case. So, we cannot say. All right. So, all right. So, I will talk about affine Kac-Moody Lie algebra. I will be talking about non-twisted affine Kac-Moody Lie algebra. So, basically these Lie algebras can be described entirely in terms of a finite dimensional simple Lie algebra. So, if we have a finite dimensional simple Lie algebra, we can construct its loop algebra and then we take the central extension and then we attach a derivation. So, that is how the construction goes. So, let this L, it is a Laurent polynomial ring in one variable. Let this be a Laurent polynomial in the variable t. So, what are the Laurent polynomials? So, Laurent polynomial, say Pt, this is summation Ck t raised to power k, k belongs to z, and only finitely many of these Ck's are non-zero. Okay. So, only finitely many Ck's are non-zero. What about the residue of this? Residue of a Laurent polynomial, what is it? C minus 1, which is coefficient of t raised to power minus 1. So, residue of Pt is C minus 1, which is coefficient of t raised to the power minus 1. So, this is what? This is a linear functional on L. Okay. So, this residue is a linear functional on L. So, what about residue of d? If we consider any Laurent polynomial and we take the derivative, then what is the residue? Zero, because in this case we do not get any term containing t raised to power minus 1, because we are taking the derivative. Yeah. And residue of T inverse is only 1. Okay. All right. So, now before defining a loop algebra, we define a bilinear complex valued function phi on L by, so we take two Laurent polynomials P and Q and we define it residue of dP upon dt q. So, this is a bilinear complex valued function on L. And what are the properties? It satisfies certain properties. Phi has the properties one can check this phi of PQ is equal to minus phi of QP. Okay, so another one is phi of PQR plus phi of QRP plus phi of RPQ is equal to 0. One can check these two properties. Okay. Okay. All right. Now, I talk about loop algebra of a simple finite dimensional algebra. So, let G naught be a finite dimensional simple Lie algebra over C. Okay. So, then we consider the loop algebra of G. Loop algebra of G naught, which is we denote it by LG naught. This is the loop algebra, and this is L tensor with elements of G naught. Okay. So, what is this? This is an infinite dimensional complex Lie algebra. Okay. So, LG naught is an infinite dimensional complex Lie algebra. And what is the bracket here? With bracket, so if consider two elements, so we call it P tensored X, Q tensored Y. We are denoting this bracket by this naught. So, this is PQ tensored X bracket Y. X and Y are elements from G naught and P and Q are elements from L. So, these are Laurent polynomials and these are elements from G naught. So, P Q belongs to L, X Y belongs to G naught. So, this is the bracket. Okay. So, with this bracket, this loop algebra is an infinite dimensional complex Lie algebra. Okay. Now, on G naught we have a symmetric non-degenerate complex valued bilinear form which always exists. So, and it is unique up to a constant multiple. Okay. On finite dimensional simple Lie algebra, yes, Killing form. So, we can always have that form and that will be up to a constant multiple, it is there. So, we can extend that bilinear form from G naught to LG naught. Okay. So let us see that. So on G naught we have a non-degenerate symmetric complex valued bilinear form, and which is unique up to a constant multiple, and is unique up to a constant multiple. So we call this form this. Okay, so now we extend this bilinear form, so this is, we extend this to an L valued bilinear form which we denote by this. This is the bilinear form on L G naught. And what is this form? So this is, if I take two elements P tensor X, Q tensor Y, then this bilinear form is PQ XY. Okay. So P and Q are elements from L, and X and Y are elements from G naught. Okay. We have extended the bilinear form from G naught to L G naught in this way. If I consider two elements P tensor X, Q tensor Y, and define the bilinear form as PQ, this is PQ X bilinear form Y. Alright, also we extend every derivation D of L to a derivation on L G naught. So also we extend every derivation D of L to a derivation on L G naught. So if I consider one element from here, so this is P tensor X, so this is dP tensor X. P belongs to L, X belongs to G naught. Okay. All right. Do you know what is a complex value 2 cocycle on a Lie algebra? Yes? Anybody? Okay, so huh? Oh, definition they know. Okay, so I can straight away define that complex value 2 cocycle, or shall I state the definition?
Maybe you can just recall that.
Okay, all right. Okay, so a complex valued 2 cocycle on a Lie algebra G is it's a bilinear complex valued function psi such satisfying these two properties. Psi of AB is equal to minus psi of BA. Second one is psi of A bracket B C plus psi of B bracket C A plus psi of C bracket A B is equal to 0 for A, B, C belongs to the Lie algebra G. For A, B, C belongs to G. So, this is a bilinear complex valued function which satisfies these two properties, and so now on this we define a complex value 2 cocycle. So, on LG naught, on our loop algebra, we define a complex valued 2 cocycle in this way. Psi of say A, B, this is residue of dA upon dt B, and this is the bilinear form. So what we are considering, so this is an element from LG naught, we are taking its derivative and then we are taking its bilinear form with B, and then we are taking its residue. So we will check that this is a 2 cocycle on LG naught.
This derivative will be extended to LG.
Yes, yes. So actually, so this A, suppose A is our P tensor X, B is Q tensor Y, right. So this is residue of, so we are taking this derivative, so this will be just dP upon dt tensor X, and this as it is. and if we are considering our this bilinear form, so this is just residue of dp upon dt q x bracket y. Okay. And we have just defined one function phi. So, this is just phi pq. Okay. So, this is just phi pq xy. We will check that this is a 2 co-cycle. So, we have to check these two conditions 1 and 2. So, let us check that. Okay, we can check it on the generator. So, we will check these two conditions. All right. So, check that this psi is a 2 co-cycle on L G naught. So, first one, so we have to see, so we will check this on the elements of the kind P tensor x, Q tensor y. P and Q are coming from L, X and Y are coming from G naught. So, this P, Q belongs to L, X and Y are coming from G naught. So, what is this? So, this is residue of the derivative here. So, which is dP upon dt tensor x and Q tensor y and this bilinear form. So, this is residue of dP upon dt q and bilinear form x y. This is only phi pq. So, phi of pq. This I have defined earlier. So, and what properties this phi satisfies? Phi of pq, phi of pq is minus phi of qp. Okay. So, because of that, and this is symmetric. This is a symmetric bilinear form. So, so first property is okay, isn't it? So, this is same as, so we can write this as minus phi of qp, okay, and this is symmetric. So, we can write like this, and this is nothing but psi of q tensored minus psi of q tensored y p tensored x. So, first property we have checked. First property we have checked. We have to check the second one. Sorry? This is a property of this phi function. We have just stated it some time back today. So let us check the second one. So, how do we check that? So, psi of, we will consider elements of this type P tensored x, P tensored x, Q tensored y R tensor Z, okay, plus psi of Q tensor Y R tensor Z is with P tensor X plus psi bracket of these two and then here Q tensor Y. So, we have to show that this is equal to 0, where PQ, where P, Q, R are elements of L and X, Y, Z are elements from Z naught. So, can we see this? Will you try it now? Was it done? This was done. And sorry? Jacob, no, we tried. So, you can make use of this. You can make use of this. So, all right. So, what is that? This is so psi of yes PQ tensor X bracket Y R tensor Z, which is again, if we make use of that, it is simply phi of, this is simply phi of PQR and X bracket Y with Z, this bilinear. Yes, this one is okay. Similarly, second one will be what? So, second one will be psi of QR tensor Y bracket Z P tensor X, and this is simply phi of QR P and the bilinear form YZ X. And what about this? This is plus, so we are going, this is psi of, so first this psi of, sorry?
You can directly write.
Okay, we can write directly here. So, this will be phi of RP Q and the bilinear form Z bracket X Y, right. So, now, so we want to take this term out somehow. So, we have to use the symmetric and invariance property of the bilinear form. So, what is this? This is, we want x bracket y. So, use the symmetric property here. So, this x, y bracket z, and again use the invariance property. So, x, y, then z. Okay. And here what we are getting here, what is this? So, we want x, y. So, first we use the symmetric. First x, y, we want x, y, right? First we use the invariance and then the symmetric property. All right. So, what we have got, so finally what we have got is x, y bracket z, and we have got inside the bracket phi of PQR plus phi of QRP plus phi of RPQ. This we have got, and this is 0. This is 0. Okay, I wrote it before. So, this is 0. So, this is whole thing is 0. Okay. So, we have proved that this is a 2 co-cycle on LG naught. On our loop algebra, this is a 2 co-cycle. So, we will consider the central extension of LG naught, which is one dimensional and associated to this 2 co-cycle. Okay. And then we will adjoin a derivation d, which will be acting as T d upon dt on LG naught, and on k it will be acting as 0. Okay. So, we will be talking about central extension of LG naught, and then we adjoin one derivation that will be called LG naught, L hat G naught, which is, so this is LG naught plus k. Here k is the center, one dimensional center, plus CD. D is this derivation, and with this, and I will define the bracket. So, that becomes a fine Kac-Moody algebra. So, I will continue from here tomorrow. Yes. So, we have proved that this is a 2 co-cycle. So, associated to this 2 co-cycle, I will adjoin one dimensional center. All right. So,